Yes.
Yeah, we can
Awesome.
see that.
Thank you, Jerry, for the nice introduction and the kind invitation to present at this very nice webinar series that you started last year. And good morning to everybody from the West Coast and everywhere, wherever you're present. And thank you for attending this. So I'm going to talk to you today about TD-DFT work that we've actually done to study molecules and materials, especially applied to Xray spectroscopies. And I will illustrate that with recent applications and developments within this framework. So just to give you some backdrop, in fact, about where we are, in fact, in the state of Washington. If you see my pointer here, I'm located at PNNL, which is in the Tri-Cities in Southeast Washington State. Jerry is at the University of Washington at Seattle here, which is about 200 miles east of us on the other side of the Cascades. And this is an aerial view of PNNL along the banks of the Columbia River just a few years ago. There's more development that's happened since. And this is our neighbor, in fact, LIGO Hanford, which happens to be located in Tri-Cities as well. If anybody visits the Tri-Cities when travel is open, I encourage you to visit LIGO Hanford for an open house tour. It's awesome. So all the work that I'll be presenting today is based around the NWChem Computational Chemistry Suite, which is an open source code that is developed at PNNL. And we have an open source code and we host the code on a GitHub site. The link is provided here. And we wrote up a review article last year in JCP, which summarizes the overview of all the various capabilities that are there in the code. So all the work that I'll be showing today is essentially based around the Gaussian DFT and TD-DFT modules. And specifically, it's the linear response TD-DFT module, because we also have a real-time TD-DFT module as well, which is not the context of today's talk. So here is an outline of the talk. I've divided the talk into 3 bits to illustrate various areas that we've looked at. And as per Jerry's advice, I will provide a break at the end of each of these parts and then finish up at the end. So the first part, I'll talk about XANES, the near-edge XANES specifically, and I'll illustrate that with some work that we've done recently with our collaborators at Oregon, looking at the photoaquation of aqueous ferrous hexacyanide, following which I'll talk to you about some really nice work that's still yet to be published on transient iron K-edge XANES in aqueous iron to iron 3 mixed valence complexes in solvent. And then finally, I'll show you some recent work that we've done going to the L3-edge XANES for ruthenium models for complexes. And then followed that, I'll be talking to you about work on valence-to-core Xray emission spectroscopies. And then I'll wrap up with resonant elastic state scattering developments within the TD-DFT framework that we've just recently published earlier this year. So this audience doesn't need an introduction to X-ray absorption spectroscopies, but I just threw it up here sort of just to give you a sense of a high-level view from an X-ray theorist standpoint. So typically, these edges are divided into K edges, L edges, M edges, and so on and so forth. And for most part, the 1s states that are essentially excitations of the 1s levels are the K edges. Theories like beta salpeter, TD-DFT, DFT-based approaches, in fact, do pretty well at these kinds of edges. In fact, although there are corner cases that we occasionally we encounter, and care has to be taken to address those issues. But as you go towards shallower and shallower edges, and because of the spin-orbit splittings as well as multiplet effects, you typically tend to have to treat the electronic structure with a multi-configuration approach, and the computation complexity also grows as a result. So there is from a theorist standpoint, there is always this need to try and find sufficiently accurate, moderate cost methods that can actually be useful to interpret X-ray spectroscopies. And that's the philosophy that I follow, in fact, trying to see how much you can get with a cheaper theories in principle. So the linear response TD-DFT module in NWChem can also address X-ray spectroscopies. And the way we've done this essentially is we have extended the Davidson solver in NWChem to seed the Davidson solver with the core level states with a model space that includes the core states or the core orbitals that are actually involved in the core excitations. And essentially, once you start with this model space, you can solve the TD-DFT response equations. And And the solutions of these TD response equations are essentially your XANES excitations. And as you go higher and higher in energy, you start getting into further and further energies out. But typically within the Gaussian framework, you typically are interested in the pre and near edge features. So to illustrate this work, I would like to talk to you about this photoreactivity of aqueous iron hexacyanide. And I'd like to point you to a talk given by Anne-Marie Mach from the APS on June 1st, 2020. She talked about the system from an experimental standpoint and the challenges that they had to overcome from a synchrotron perspective to tease out the necessary dynamics. And so we did the theory parts for that project, and she talked about that briefly. So I'll get into a little bit more detail here and show how our capabilities were able to unravel some of the underlying dynamics. So at a high level, there are two processes involved, in fact, in this photoreactivity mechanism. The first one, which is less than 330 nanometers, less than 330 nanometers, you get a photooxidation process. And it's known that beyond 330 nanometers, the photoaquation process is the dominant mechanism, which essentially says that you shine light on the system goes into an excited state. And then what ends up happening is the system ends up losing one cyanoligand and it's replaced by one of the waters in the bath. And then you end up getting a aquated system with one CN left out. So we were interested in understanding the dynamics of this whole process, in fact. And we were helped by a very nice paper written by Michael Reinhardt and co-workers in 2017, where they sketched out a very nice mechanism which they thought was played the key role in this whole aquation process, in fact. And this gave us sort of I would say, a framework within which we could work and try to unravel the details of the dynamics. So essentially, we were after this process. If you shine light on the system, what really goes on before you end up with an aquated system? So to put things in context, we had to evaluate our own theories to make sure that, because we were using Xray probes, our collaborators were using Xray probes to tease out the mechanism. So we had to make sure that we were actually in a good place theoretically, especially we were looking at the iron K-edges in this case as the probe to monitor the dynamics. So in fact, we were in a good place, in fact, because when we were well positioned for this problem, because just a year before that, in 2018, with Munira Khalil and her group, we published a comprehensive paper on iron 2 and iron 3 hexacyanide model complexes, going all the way from the infrared all the way to the X-ray spectrum, including the valence-to-core as well. So we were pretty confident that, if you look at the characteristics of the system, for example, and many of you in the audience might be familiar, if you look at the Fe2 system, you actually have a low spin system here. And if you excite from the 1s, you essentially get a feature which we call the B feature. And in the case of Fe3+, you have a case where you have an empty orbital and basically a half-filled orbital in the T2G, in fact, which gives rise to this A feature as well as the B feature that you end up seeing in the experiment, A and B features. So to remind you, both these A and B transitions are, in fact, quadrupole transitions are now very weak. So the theory was able to, experimentally, the A and B features are split by about 3.3 electron volts. And with our level of theory, that we were able to predict the 3.6 electron volt splitting, which was actually reasonably well given the fact that you have to choose the appropriate exchange correlation and so on, especially with DFT and TD-DFT calculations. We were pretty satisfied with this agreement. And note that these calculations were in fact done in a QMMM environment where we treated the solvent explicitly with molecular mechanics environment, and the transition metal complex was treated quantum mechanically. So this actually set us up really well to understand this photoaquation process. So going back to this paper that I mentioned earlier by Michael Reinhardt and co-workers, they had proposed a mechanism, in fact, where the system initially is excited. The Fe2+ system is initially excited, then it undergoes there's an early time scale where a cyanoligand is actually lost, and then followed by a longer time scale where the water is in fact replaces the missing cyano part. So we are still working on this early time scale, and we have a project ongoing with our collaborators at SLAC and APS. So we decided to focus on the latter mechanism, in fact, like assume that the system is already on the triplet state, which is the mechanism they propose. They propose the system, in fact, gets excited from a singlet to a singlet, then there's a quick transition for a triplet, and the system evolves on the triplet, a cyano ligand comes off, and then the system evolves for a long time, and then a water comes and replaces the spot where the cyano left. So while we did the dynamics, we realized that this five-fold coordinated system was not necessarily just one structure, was actually it was a set of two structures that were interconvertible and oscillated between a timescale of about 3 picoseconds. So what that means is that the XANES spectrum that was being measured by the experimentalists was some kind of a combination of these two. So theoretically, of course, you have good control over these structures. So we were able to simulate the XANES spectrum for the square pyramidal as well as the trigonal bipyramidal structures, and you find the pre-edge features that match quite well, in fact, with the experiment. And unlike the model complex plots that I was showing you in the previous slide, these are in fact dipole dominated, in fact, because you've got orbitals, you've got a hybridization between the d orbitals as well as the missing ligand, in fact. So it's actually dipole dominated. So you in fact get a prominent peak earlier on in the pre-edge region. So we were also able to simulate the long time behavior, in fact, with the water present in the system and with the water replacing the cyano ligand. And our XANES results were also in very good agreement here, in fact. But this is all very good, but we also wanted to understand how well these features were borne out from the theory in relation to the model complex. And so we wanted to understand if the shifts with respect to what we call the reference model complex was also in the right place as far as theory was concerned. So on the top here, I show you the ground state model complex with this B feature that I told you, because there was only one excitation from the 1s to the EG orbitals. The subsequent panels here essentially are these transient species that you encounter in this photoaquation process. And you note that, that there is an overall redshifting about 2.5 EVs away from this reference compound once you go into this five-fold coordinated system, and which is in fact borne out by theory, in fact. And likewise, in the aquated system, you get a redshifting about 1.5 electron volts, and which is also really there, in fact, because so we were pretty pleased with this whole thing, in fact, with this whole mechanism coming into place. So we were pretty confident with this whole picture that was unraveling with our simulations. So what does that say about this long time behavior of 20 picoseconds, right? So we had all this dynamics data, and we were interested in understanding why it took so long for the system to aquate, because which of these isomers, in fact, of these structures were actually the one implicated in the overall dynamics. So if you look at it carefully, you have this the trigonal bipyramid and the square pyramidal. The square pyramidal shape is the only structure that allows a CN ligand, a water to come and attach itself to the ion center. And we know that there is a 3 picosecond interconvertible regime where these two systems oscillate with each other. So what we decided to do was we tracked the order parameter, like a five-fold order parameter of these two, and tracked this across the whole trajectory for this entire 3 picosecond oscillations. And we found that the system resides in this conformer for close to 85% of the time, and only 15% of the time in this conformer, which clearly tells you that there's a probability issue here, and this offers a very small window when the water can come and attach itself. And then it gives you a mechanism for why this overall 20 picosecond comes into place. So this was actually a very nice work. Like I was telling you earlier, there is also this early time scale T1 where the cyano ligand is coming off the system from the triplet state. That is work that is ongoing because we're simulating that data, and we're waiting for experimental data because we need better resolution on that time scale. And for details of this work, I refer you to this paper that was published in 2019. So moving on to another system that we've been looking at recently with Munira Khalil and her group at the University of Washington. I point you to another global XAS talk by Elisa Biasin a little bit over a month ago, where Elisa talked about the same system, which is this iron-2 Ruthenium III mixed valence complex in water, which undergoes and metal-to-metal charge transfer state followed by a very fast back electron transfer on the order of about 65 femtoseconds. And she talked about the ultra-fast scattering studies that we did on that work. So this particular slide shows the electronic side of things. So the system undergoes, so we have an ion 2 and a ruthenium, we have an ion 2 and a ruthenium 3 on the ground state. And when you shine light, which is in the near infrared, you essentially get an electron transferring from the ion 2 to the ruthenium, which makes it an ion 3 and a ruthenium 2. And this process is extremely fast. So what we were able to do in this case, because using the same protocols we established, like I was showing you in the previous sets of slides, we were able to, in fact, run the excited state dynamics on this. And we did this within the context of TD-DFT gradients. So what you do there is you allow the system to evolve on this metal-to-metal charge transfer state, and then you basically harvest structures from this excited state. And then once you have these structures on the excited state, you essentially prepare an excited state determinant from which you can do K-edge XANES calculations. So TD-DFT calculations can also be done from an excited state reference if you know how these how to prepare these excited state references. So traditional TD-DFT calculations are done typically on a ground state reference, but this is a nice illustration of a case where we had an excited state reference where we had this system with the electron moved over to the ruthenium, but on different structures, in fact, along the MMCT state, and we were able to probe the K-edge along that trajectory, in fact. So if you look at the left side, you see a close to a ruthenium, an ion 2 and a ruthenium 3, which is close to the ground state of the system. And as the system evolves, you see a little A peak start emerging from the system on the side here, which is representative of this Fe3-like situation. Of course, it's not a pure Fe3-like because this is sitting on a very ultra-fast charge transfer state. We looked at a number of plots, number of hole densities along these trajectories, and we were able to plot this A minus P energy difference with respect to the whole charge. And we found that it actually fell on a straight line, which allowed us to use this as a ruler. So just for reference, the ion 3 model complex is the star right on top here. And we found that this 0.6 whole charge, which corresponds to this feature here with an A peak just basically peeping out, was the best fit to the experiment. So a version of this manuscript is on the Chem archive, and we're actually polishing up this work to be submitted. So other selected K-edge works that we've looked at in recent years involve also include the aluminum K-edge, where we've looked at that at a Bronsted acid site in a zeolite, which is very relevant to catalysis. We've looked at the hydrated structure of aqueous Na+ at the sodium K-edge. We've looked at supersaturated calcium carbonate at the calcium K-edge, sulfur K-edge for lithium sulfur batteries. And most recently with Munira Khalil and her student Caroline Lowe, we've looked at the transient nitrogen and oxygen K-edges to tease out the ultra-fast excited state intramolecular proton transfer. In fact, this paper was just accepted, and it's beautiful work, in fact. So moving on from the K-edges, we looked at our approach to see how we could tackle L-edges as well. And there are certain things you must keep in mind with L-edges, because L-edges are spin-orbit split. And in fact, so you have a 2p3 halves and a 2p half states, in fact, involved. So in this particular case, we used our approach to look at the L3-edge of ruthenium model complexes. And we had some very nice data from our collaborators at SLAC that allowed us to compare what we had done. And on the right side, I've given you the experimental plots, which have again used this A, B, and C labels, which correspond to excitations into the T2G, B, which represents the excitations into the EG, as well as C, which is basically into the pi star, into the ligand orbitals. And as you can see on the left, and as you see the comparison between these two, you see that the calculations, in fact, bear out every single feature in the experiment, which gives us real confidence that this actually works really well. I should point out that this approach, we've only accounted for scalar relativistic effects. We haven't included any spin orbit effects in the core or the valence, because in the valence, the 4D spin orbit is only about 0.1 electron volts. So even though it's qualitatively missing some of the rigor that's required to treat L edges, we're able to in fact see that this approach is able to tell you something meaningful about the experimental data. So with that, I'll stop here and see if anybody has any questions in the first part.
Okay, so there was one question, which is what is the difference between TD-DFT and a DFT relaxation?
TD-DFT and a DFT relaxation.
Right. Maybe just say a little bit about what the difference between TD-DFT and DFT.
Right. So in a nutshell, thanks, Josh. So in a nutshell, DFT is a ground state approach, and TD-DFT is essentially the excited state extension of DFT. So when, of course, you could, in typical fashion, you normally in the ground state, DFT is typically used in the ground state, but of course you can also do DFT with core holes present in it, which kind of gives you an excited state variational solution. But in a broad brushstroke, DFT is a ground state theory and TD-DFT is the excited state version of that, if that helps. Yeah.
Okay. And then Jerry had a question. Sorry, hang on one second.
Oh, sorry.
There we go.
I was curious, what's the magnitude of the computational support needed for the calculations? What sort of things can you do on a desktop, and what things really need supercomputer nodes?
So these things, in fact, could be done with a few nodes. These calculations, like these Ruthenium L3 edges, because these are relatively small systems. For example, if you want to study some of these larger systems, like I was saying, for some of these systems, for example, this is if you try to look at what is dressing this this transition metal complex, you get around about 250 atoms. So you really need to go beyond desktop in this case. You need some computer resource, real serious computer resource for these things. So the model complexes, I would say, few nodes. These larger complexes, depending on what you're trying to study, especially if you go to a couple of hundred atoms, because these can be quite strenuous calculations.
And there's another question asking about whether you're basically modeling just one electron processes.
No, not really. I mean, so if you want to call it that, TD-DFT is a theory of single excitations, if you want to call it that. So, yes, I mean, if you're looking at it from a point of view of a single excitation of a single electron being moved between excited states, that's correct. But of course, the nature of the excited state matters, because if you look at a specific excited state, let's say we pick an excited state here. TD-DFT, in fact, gives you an excited state representation of that, which is essentially a superposition of several slated determinants potentially with superposition coefficients. So even though in the simplest approximation, you essentially have, say, an electron exciting itself, you can have a single electron excitations, but your excited state could be composed of several singly excited determinants. So it could be a multi-determinantal type composition. So TD-DFT gives you a richer picture of things. But surely multi-excitations are not included in TD-DFT if you're asking about that. We don't have double excitations in TD-DFT. That's by construction. That's not included.
And the extent to which multiple determinants are really included depends quite a bit on depends quite a bit on the exchange correlation kernel, correct?
Exactly. I mean, so traditional exchange correlation, which don't have any frequency dependence, of course, will not give you double excitations. But if you, even within the context of what we call adiabatic exchange correlations, you're in the space of single excitations. But of course, the richness of the excited state is closely coupled to the exchange correlation choice, like DFT is, because TD-DFT inherits the same issues. And we don't specifically tune a TD-DFT, a functional for the TD-DFT work, because we still use the functionals that are created for the ground state onto the TD-DFT, for the TD-DFT level of the calculations. Yeah.
And then John Vincent had a question. How big do you think the spin orbits splitting needs to be before it's no longer acceptable to just add broadening?
Yeah, so very nice question. So the thing is, I'm leaving this slide on the screen here. So this particular case, we were able to get away with it because the L2, L3 splitting in ruthenium was of the order of 100 electron volts. And so we know that the spectrum there is no overlapping features between the L2 and the L3 in this specific case. And of course, the final states, like I've written here, if you're aware of the order of 0.1 EVs, we know that, so you have a you can grossly broaden out the features like you were mentioning, John. But of course, the interesting thing is, as you go to shallower, the 3D transition metals, where the spin orbit splitting, the 2p spin orbit splitting is of the order 10 EVs, for example, or less, you have to do the full two-component treatment there because you might have L2, L3 features running into each other. And as ironic as it might sound, if you go to sulfur, which is even lower than that, where the spin orbit effects are less, the L2, L3 features are even closer. So if you want to understand the L-edge of sulfur, you need to have the full spin orbit treatment because the L2, L3s get really close, and you can also have the L2, L3 ratios also can't start playing games with you because the 2-to-1 ratio doesn't hold anymore. So you can have L2, L3 start leaking into each other, and you can potentially have an L2 that's taller than an L3 when you go up to, there are well-known cases like this where the intensity ratios actually split. So in a way, we get away with this because we have strong relativistic effects with second-row transition metals like 4D, but we are also well separated in the L2, L3, so it allows us to treat the L3 by itself, which is what we've done here.
Okay, I guess I had one question as well, which is on the K-edge work. You had this K-edge. It was the second material where you did you did K-edge from excited states.
Oh.
And I was wondering how you prepared those excited states, whether it was through real-time TD-DFT or just a supposed.
So yeah, so the difficulty, I'll answer the first question. So in real-time TD-DFT, it's a little bit difficult to get the states out because everything is encapsulated into a density matrix. So it's all the information is present, but difficult to tease out from this particular thing. So what we've done here is we looked at it in the linear response context. So you can do a standard TD-DFT calculation on the ground state, examine what your metal-to-metal charge transfer state looks like. And of course, you have to pay attention to where it is. You're going to get these offsets with respect to the choice of exchange correlation. And in this particular case, we've used PB0 pretty much everywhere because it gives us a reasonable accuracy, a balanced approach, despite the errors incurred. But once you spot that, you can use orbital swaps, for example, in combination with maximum overlaps, for example, to converge a state. Because you need that core level state. You need the target states for the core level excitations that have the proper rotations between the two metal orbitals so that you can start probing those metal orbitals properly occupied. But for the geometries themselves, you don't really need the core states really, because you can use a pseudopotential and invoke a TD-DFT excited state gradient approach where you actually get the analytic gradients at the TD-DFT level to get you these excited state geometries. So once you've gotten these excited state geometries on the excited state surface, then you prepare these determinants for each one of those states that you've harvested, and then do the K-edge spectrum for each one of them.
I see. Okay, thank you. Maybe we should go ahead and move on now. It looks like.
Yeah, for the second part, thank you for the questions. These are good ones. So the second part of the talk, we'll go reverse. So we're looking at the valence-to-core X-ray emission in this case, and I'll illustrate that with a few examples as well. So again, this audience doesn't need an introduction for X-ray emission spectroscopies. As we all know very well, the K-alpha, K-beta lines are the strongest lines, but the valence-to-core X-ray emission lines, in fact, which are de-excitations from the valence orbitals to highest occupied valence orbitals to the core hole, in fact, are very, very interesting because they encapsulate information about the highest occupied molecular orbitals, and in combination with the XANES, which probes the lowest unoccupied orbitals. With these two spectroscopies, you can actually get a very, very full picture of your bonding environment. And interestingly, this V2C X-ray emission is becoming a powerful probe now at various light sources. And Jerry Seidler and his group have pioneered lab-based setups to do these kinds of spectroscopies, which is excellent. So the way we do this in NWChem is the following. So we again work within the TD-DFT response framework here. And so the way we do this is, again, it's all in how you prepare the initial reference state. So we start with a neutral ground state in this case, and then we prepare what we call a relaxed core hole ionized reference state, where we've taken out the core hole, we've prepared a core hole from the state that we want to de-excite into. And then within this model space, we solve the TD-DFT, TDA response equations using this reference state. And what you end up getting is, because everything is falling down, you in fact get a negative transition that corresponds to the emission spectra. And like I was mentioning earlier, there are approaches that tackle the same spectroscopy between an initial and a final state with a transition dipole between the two states, for example, which is sort of like in a Kohn-Sham picture, single particle picture. But we get these solutions directly from the TD-DFT solutions, which encapsulate this multi-determinantal character that I was saying, because even though core excitations tend to have very single determinant dominant characters, but that's not to be assumed. You can also get non-intuitive mixings into a specific excited state representation from Slater determinants that come from other places. So you cannot ignore these things. So this excited state framework allows you that automatically. And I refer you to this paper, in fact, where we talk about the details of how we've done this. So the first set of systems we looked at here were these 3D to 1s transition metals, because these are actually really, really nice systems where these spectroscopies work really well. And I'm not expecting you to see the fine details of these individual systems, because these are a bunch of 3D transition metals, all octahedral complexes, a mix of high and low spin. But what I would like you to take away from this is that you see an overall agreement in terms of the highest peaks. The peak shapes tend to be brought up, they're essentially borne out by the theory, which is quite nice, in fact. And you can, in fact, get the assignments from these calculations as well. And going back to these, the 4D systems that I showed you earlier for the L3 XANES, we went ahead and did this 4D to 2P transition here, in fact, for the V2C for the system, because the same group as Slack provided us this very nice data for this. So we decided to do this because essentially you're looking at de-excitations from the 4D orbitals to the 2P, and using the same protocols like I was mentioning earlier, where we've neglected the spin orbit splitting and so on, you can in fact get a really nice agreement, even with this noisy experimental data here. In fact, you get this, the dotted lines below are the theoretical spectra, and you can see that each of those features are essentially borne out by the theory. So this was a work that, this is another set of system looking at molecular and crystalline sulfur that we did with, in collaboration with Jerry Seidler, Will Holden, Evan Jarman from Jerry's group, where we looked at a broad range of sulfur compounds. And here you're looking at the 3P to 1s transitions. In fact, just to see how well the theory works out. So in fact, we started off with assessment of the theory to see how well it does. And we were really surprised how well each of these spectra were in fact reproduced. The experimental spectra is on top, the theory spectra is below, and the agreement was quite remarkable, in fact. So we went ahead and in fact looked at some solid state compounds. By solid state, I mean, because we work within this cluster Gaussian DFT, TD-DFT framework within NWChem, you have to construct a cluster with a suitable capping. You have to be careful about these things, but you have to provide a suitable capping so that you can represent the solid state environment reasonably well. And so this is zinc sulfide, where you can see each of these features are blown out. And this is, I think it's an AS2S3, where again, you see qualitative agreement between the theory and the experiment. And the worst agreement that we saw was this FES2 system, in fact, where you see that the splittings are not necessarily borne out by the theory. In fact, we didn't get into the system closely because we were looking at it from a high level, looking at the broad applicability of this approach for these sulfur systems. And I should point out that this study, in fact, spawned off a nice machine learning study that Jerry and his student Sam Teref, in fact, have led to look at combined machine learning with the K-edge XANES as well as the valence-to-core X-ray emission for sulfur. In fact, and I encourage you to look up this paper on ChemArchive. It's a beautiful paper which talks about classifications of a much bigger set of compounds, sulfur compounds. And this system, this set of system was about battery materials, where we looked at vanadium oxide. Again, these systems were essentially represented in cluster form, where we had vanadium oxides as well as lithiated vanadium oxides. And what's not said here, of course, is the care that needs to be put into creating these clusters, of course. You know, if you had a good periodic environment, then you wouldn't have to worry so much about it. But since you work within a molecular context, you have to pay special attention so you don't get spurious states from uncapped bonds from the periphery of the cluster, for example. So Evan and Will really worked hard on that. And this was a nice collaboration. I believe Josh was also involved in this work. And here you can see that, you know, overall we get the right kinds of splittings from our level of theory. We don't necessarily get the exact, you know, the peak heights in the specific case, but I would say, in fact, it's in reasonably good agreement that allows us to, you know, assign these spectra and look at assignments, of course, and provide the necessary support you need for theory. And I think there is a talk by Evan who talked about core-to-core transitions, if I remember correctly, on March 23rd, and I'm not very sure, but he may have talked about these systems in his talk. So I'm pointing you to his Global XAS talk. So finally, bringing it back full circle, I was talking to you about these transient species that I was mentioning earlier. It's always interesting, you know, when you have a theory that is reasonably accurate, can this make a prediction that you can actually pose to an experimentalist to go off and measure? So we were curious to see if these two isomers that you see, the square pyramidal and the trigonal bipyramid isomers, reveal anything different when you probe it at the valence-to-core X-ray emission type probe. And what we were surprised to see was that the valence-to-core X-ray emission spectrum looked pretty much the same with these two things. And with the fact that the system resides 85% of the time in this isomer versus this isomer, it's the slight difference that we see here between these chemical shifts is probably going to be swamped out by the majority component of these two structures. But I think it's still interesting. It's a challenge that we can pose to the experimentalists to see, you know, can you have, do you have the resolution to tease apart these two structures? So this is ongoing work which we pose to our collaborators at Arbor. So I'll stop here and take questions for the valence-to-core part.
So I don't see any questions there, but I do have a question about that iron cyanide system, and you know this question of resolving the two structures experimentally, or at least confirming your percentages, your theoretical percentages or probabilities. I was wondering if that somewhere higher in at a higher energy in the XANES you see any kind of difference there.
Oh, in terms of a scattering, in fact, like an XAF signal, for example?
Well, XAFs, I wouldn't necessarily expect a huge difference just because it would only come through the multiple scattering, since they have the same number of, but yeah.
No, that's a very good question. Never thought about it that way. No, I think it's something to think about. Yeah, thanks for suggesting that. Yeah, for sure. I mean, we've provided them with this data, and of course, I think their resolution was up to a point, in fact. So I encourage you to go and look at Anne-Marie March's paper, talk, where she talks about the experimental details very well. So they had some resolution issues with that, and in terms of not being able to pin it down, which is why we have some ongoing work still with them. But I think the suggestion is excellent. Yeah.
Let's see. There's a question here about the energy difference. What's the energy difference between those two conformations?
These two guys.
Yeah, these two isomers.
So of course, so you can't really so I can give you because this system is sitting in transient, it's sitting in a bath, so there's no one energy because it's sitting in two. We could think of it as two wells. But what I can tell you is, since it has a transit time of 3 picoseconds between the two wells, you can work it out at the back of the envelope. It's roughly about a kcal-ish. That's probably a kcal, probably around a kcal, about a kcal worth of energy going over the barrier. So the system is pretty transient, going back and forth. So that tells you that these are pretty shallow wells.
Okay, thank you. It looks like there aren't any other questions, so maybe we can go ahead and move on there.
And finally, to bring it full circle, right, I've shown you the how we've looked at the absorption branch as well as the V2C emission branch using the TD-DFT framework. This is some recent work we've looked at where we've looked at resonant inelastic X-ray scattering within the TD-DFT approach, in fact, and this was really nice, in fact, because this spectroscopy, as you all very well know, connects up the absorption and the emission and allows you to probe correlations between core electrons and valence transitions. So basically, to sketch out some background here, you know that the RIXS is a 2 photons process where the core level excited states are accessed via a resonant excitation followed by a photon emission to a lower energy excited state. So that's the broad definition of a RIXS process. And this Kramers-Heisenberg equation is essentially the central equation that one needs to use to tackle a RIXS map, for example. And the key quantities in this are these transition elements that are sitting, excited state transition moments that are sitting in the numerator. And you have a ground state that goes to some intermediate state, and the intermediate state to some final state, and you have the operators in between, which could be dipole, could be a whole series of dipole quadrupoles, and so on and so forth. Now you ask yourself the question now, how do you tackle this thing from formal response theory, an object like this from formal response theory? And if you look at formal response theory, the excited state transition moments, I should stop and take a step back. Now, when you do TD-DFT calculations, you only get transition moments from the ground state to any excited state. That's the formal couplings that you get from TD-DFT. So to get excited state couplings that are actually required to evaluate this quantity, you need excited state couplings. So the formal way to go to it is actually quadratic response theories. And these excited state transition moments actually appear as double residues of a quadratic response function, and which I've sketched out what the expression looks like here. But there is an issue with quadratic response theory, especially in the context of approximate theories. So we all use approximate theories, whether it's Hartree-Fock or density function theory or some level of wave function theory, but approximated because the exact theory is not numerically tractable. But it's been shown that quadratic response theory, in fact, has a spurious pole structure. In fact, you get an extra pole in the denominator that has absolutely no equivalent in exact theory. And I encourage you to look at this paper by Dalgaard from 1982, who discussed this in the framework of Hartree-Fock theory. And there's been more recent work analyzing the same question with respect to DFT and so on, and other wave function approaches. In fact, the spurious pole structure is always present. So we asked a different question. So you run into this landmine issue, especially if you try to implement quadratic response theory, let alone the computational cost of quadratic response theory, which can be very prohibitive. So we asked a different question, saying, can these matrix elements be calculated from TD-DFT, for example? We don't have a formal wave function within TD-DFT, but we do have these solutions, the X and the Y solutions that you get from solving the Casida equations. And can you compose an excited state transition moment using these quantities? And the answer is yes, you can approximately do this. And what you end up missing is the second order polarization density relaxation in quadratic response. You actually make a mistake by doing it this way. And in simple words, I call this the uncoupled approximation, because quadratic response gives you another extra term that's present in the theory. So let's see how well this does, because we were able to compose these excited state couplings and plug it back into the Kramers-Heisenberg equation. And so here I show you 3 maps of these 3 ruthenium systems that from the set of ruthenium systems that I've been showing all along, where we actually had really nice data from our SLAC collaborators. And the top shows you the RIXS map, where you have the energy transfer on the y-axis and the absorption energy on the x-axis. And the bottom graphs are essentially the cuts along these dotted lines, which correspond to different incoming photon energies. And as you can see, the energy transfer for non-zero energy transfer, in fact, the theory, in fact, does quite well. In fact, we were pretty pleased to see this. In fact, there's almost pretty nice agreement with one-to-one agreement with all the features that are present. The dark line being the experiment, and the lighter line below is basically the theoretical prediction based on how you cut through this map, in fact. The only issue that you might have noticed here is the elastic point line. The elastic line here in fact, the intensity of the elastic line is actually largely different compared to the experiment. We overestimate this. Theoretically speaking, the elastic line is essentially, you basically have, both these elements are essentially the same. You essentially have a mod square sitting in the numerator. So from a theoretical standpoint, it's very easy to calculate, but we believe that there's other physics that we're missing, in fact, in the theory that doesn't bear out these small features that you see, the really short elastic feature small elastic feature that you see in the experiment. And maybe there are uncontrolled experimental effects as well that we're not, but of course the interesting physics is always in the non-zero energy transfer, which is where the rich correlations between the core and the valence states come together. So this is a broad swath of actually a larger set of compounds we looked at, published in this chemical science paper. And what I should point out, in fact, is for some of these calculations, we needed of the order 100 core level states and of the order of 1,000 valence states to, in fact, evaluate these maps. Now, if you put that in context of how this could be achieved with quadratic response, it's probably very, very difficult to do this. So these calculations were done pretty much at the cost of roughly 2 TD-DFT calculations, one for the core states, one for the valence states, and then you apply this the simplified approach that we've got to couple the 2 states together and helps you calculate the Kramers-Heisenberg relationship. So the point is, we may be missing some physics with this approach, but it's giving us enough to interpret the experiment, and I would call it a pragmatic approach. It's not perfect, but it's still very useful. So in summary, I've shown you how the approach that we've got, linear response TDD approach, it's almost black box type approach that we've got in NWChem that allows you to look at both XANES as well as the valence-to-core. And I've shown you illustrated those implementations with a bunch of applications. And of course, even though we've neglected the spin orbit splitting in the ruthenium complex, for a full treatment, especially for the cases I was mentioning to you earlier, where L2, L3 ratios could be quite different, you need a full treatment. I mean, there's no getting around that, of course. And so we kind of worked around it in a special way in the specific case. And so that we have an ongoing project along those lines. And then the simplified TD-DFT approach is pretty encouraging, in fact, because we were able to tease apart these experimental features for a very complex spectrum, in fact, using this simplified approach, which I think is quite encouraging, in fact. And so, of course, trying to generalize that to include spin orbit effects, it's a project that's ongoing. With that, I'd like to acknowledge my collaborators at PNNL, UW Seattle, Munira Kalalana Group, SLAC collaborators, Argonne, University of Seattle Physics, Jerry and his group, and UC University of California at Irvine, and all the names that I've underlined are people whose work that I talked about today, collaborative work that I talked about today. And with that, I'll take questions if there are any further ones.
Thank you very much, Niri. I do have a question about the RIXS. I was wondering, there are some benefits to doing real-time simulations. I was wondering if there's any serious barrier to doing a real-time RIXS or with TD-DFT.
The real-time.
Just in the sense that I know that some of these I guess what I would say is simulation of pump probe experiments become somewhat easier with real-time TD-DFT than, and so, but I haven't seen that with RIXS, and I know that.
No, and you hit the nail on the head, and something that
difficult.
I was thinking about myself. It's all about composing this object. You need, and so I think, for example, going along what you said, if you start with a density matrix representation, the information is all there, except that it's bundled into this density matrix and it's hard to tease out of it. So, like, as you know very well, there are two different implementations of real-time propagation. You can propagate the cone-sham states, or you can propagate the density matrix, or you could do Green's function propagation like you've been doing with John, for example. But the tricky part is here you need the individual states, in fact, to get this right. Because the way the Kramers-Heisenberg is formulated, the working equation is in terms of the states. So it's easy to do that. So I think you need sort of an alternate Kramers-Heisenberg reformulated in terms of a density matrix, for example, or a Green's function or something like that. I think it can be done. I don't think it cannot be done, but I think you just have to work harder. So, yeah.
Okay, did anyone else have questions? Okay, so Matthew Marcus asked.
Question?
Sorry?
A question?
So, Jerry.
The question is, what is meant by real time? Is it tracking the evolution of a wave function then Fourier transforming? Yep.
So that's right. In fact, that's in a broad brushstroke, that's correct. So literally when we say TD-DFT, it's kind of ironic because what information you get out of a TD-DFT calculation is in the frequency domain, even though it's got time-dependent density functional theory. So the true nature of the time dependence can only be done by propagating a wave function or a density matrix where you literally have a real-time propagator and you propagate in time, you hit it with a pulse, and you see what the system does. So the way you've thought about it is correct. So sometimes if you want real-time information out from a frequency domain curve, from a frequency domain implementation, it's essentially like an infinite time integration, right? So you've lost all of that richness. So if you want explicit time detail, you literally have to do it in real time. So.
And just to if I can add something, the benefit of that real time versus frequency space is that you can go beyond linear response just by increasing whatever pump you're using to,
yep.
You actually put the electric field in as the pump, and that can give you nonlinear response basically
right.
without doing anything. Whereas in frequency space, everything's formulated in terms of linear response, or like Neri showed earlier, quadratic response.
So one thing I will add, Josh, to that is, working within the context of DFT and TD-DFT and probing using strong fields. The thing that we forget about is the boogeyman, the exchange correlation boogeyman. As the exchange correlation becomes really strong, the field becomes really strong, memory effects might start creeping into the exchange correlation, and we kind of just sweep that under the rug and use sort of LDA or one of these adiabatic exchange correlations. So yeah, there is, we have to pick your poison in a way, right? So how much of it are you losing by using an adiabatic representation for the exchange correlation? But yeah, point well taken. Yeah.
Okay, well, if there aren't more questions, we do have a little bit more time, but thank you, Neri, again. And
thanks. Yeah, thanks for having me. Yeah.